Hello, everyone. Welcome. Thank you for joining our session. I'm Annie, your host, and I have Semab Tariq with me, our in-house PostgreSQL consultant, who will be conducting today's webinar on pgvector, how to transform your search capabilities with AI. Before we dive into it, let me remind you that you can share your questions or comments using the chat box or the QA feature. We are going to have a question and answer session at the end of the webinar, so feel free to drop your comments or questions there. All right, then. Over to you, Samab.
All right, thank you. So this talk is about how you can transform your search capabilities with AI. And the tool that we are going to cover is pgvector. So before we get started, a little bit about me. So the name is Semab Tariq, and so my professional career started back in 2017 when I first joined a local software house in Pakistan named Trading Icon as an Android and web developer. My first interaction with Postgres was in 2018 when I joined Second Quadrant as automation engineer. And at Second Quadrant, we used to build Postgres installers and CUDA installers for community. And later in 2020, Second Quadrant was acquired by Enterprise DB, and I moved there and proceed my career as DevOps engineer. And at second and at Enterprise DB, we used to do a lot of different things, different cool things with Postgres. I recently joined Stromatics, and at Stromatics, we are focused to provide professional services for Postgres, like higher availability, performance tuning, monitoring, and backups and recovery. So let's get started with our talk. So this is kind of an agenda, what we are going to talk, what we are going to cover in this webinar. So first we will see what is pgvector and what are the different fundamentals and terms used in pgvector or especially AI. And then we are going to talk about workflow search techniques and indexes used in pgvector. And then we will see how you can, of course, improve your searches with the RAG, with the help of RAG in pgvector. And finally, we will conclude our talk with discussing a couple of use cases and alternatives to pgvector. And finally, we will have a question and answer session. So first thing first, what is pgvector? So pgvector is simply an extension for Postgres. Now, if you are wondering what is an extension is simply a piece of software that provide additional functionalities inside your database, or particularly Postgres. And it in particularly Postgres. Okay. So of course, we can work with vector data with the help of pgvector, and we can store higher dimensional vector data with the help of pgvector. Now, if you are unfamiliar with the vector data, don't worry, we will get back to it in our next slides. And of course, we can store original data alongside with the vector data with the help of pgvector. So let's now discuss what exactly is vector data. Vector data is a specific way used to represent original data using numbers. So our original data can be in a form of text, images, audios, or videos. And our original data gets converted as huge multi-dimensional array of numbers. Now, in our day-to-day life, we usually work with the single, 2, or 3-dimensional data. The examples could be temperature, which can be measured in single dimension, map that can be measured in using 2 dimensions, and motion tracking that can be measured in 3 dimensions using X, Y, and Z coordinates. But when we talk about huge multi-dimensional data, that data can have like thousands, 10,000, or even more than 50,000 dimensions as well. Example could be a T-shirt that can have multiple dimensions like a height, width, color, type, and length, etc. So a particular this t-shirt can have eventually multiple dimensions. So we call it multidimensional data. Uh, and one thing is for sure that the higher number of dimensions we have for against of any product, or in this example of t-shirt, we eventually ends up having better understanding of data. So the higher dimension we have for our product, the better understanding we get for our against our product. Um, so there is a pro and there are pros and cons linked to having more dimensions or having less dimensions. So for example, if we have more dimensions for our data, that would eventually mean that we can have more data points to compare, and we can have, of course, more accurate searches, which is a nice thing to have. But the downside is the time consumption to perform searches would be can be huge, and also complexity. Also, the more dimension can add complexity and computation power, and of course, it can also add time to generate the embeddings. Whereas if you have less dimensions for your data, that would eventually means that you have now less data points to compare, and you can end up having less accurate searches. So it's always so if we are working with the vector data, we have to always find a perfect balance between having more accurate results, or having or we can focus on achieving more performance. So if accuracy is concerned, maybe you can go with having more dimensional data, and if performance is your concern, then maybe you can have lesser dimensions data. Now let's talk about what are the embeddings. Embeddings are the specific type of vector used in machine learning. Um, Oh, yeah, our yeah. We train machine learning model in our original data. So we have our original data that I just talked about. Our original data can be in a form of images, text, audios, or videos. So we have our original data. We use a machine learning model to actually train it on our original data. And so, for example, if our original data has a is a our original. So for example, if our data type of our original data is text, so this machine learning model eventually try to understands important words, topics, or grammatical features inside our original data. So if our original data type is images, then this model can eventually try to understand shapes, color, texture, or objects inside this image. Let me quickly go to my terminal, and we will see how a real world embedded vector actually looks like. So I'm on my terminal. I have created a pretty simple Python file named getembeddings.py, and here I'm using a package provided by OpenAI, and eventually OpenAI is the one who provide embedding models, and you can see I have mentioned this embedding model named by OpenAI. So the my simple string is Earth is 4.54 billion years old. So this is my original string that I am going to generate the embeddings for. So if I just run this file python3 get.py, uh, it it eventually hits to OpenAI or to this embedding model, and they pass this string to this model, and this model eventually get back to generate the embedding and send back to us. So all the numbers you see on your screen, all the floating point numbers on your screen are your embedding. So if I just highlight this and go all the way down till end, so this all data is your embedding. This is just embedding for one simple sentence, which is Earth is 4.5 billion year old. Now we can just copy this embedding and paste inside our Postgres table. So back to the slide. Um, Yeah, so data that represent similar will have similar looking embeddings as well. So, for example, cat and lion, we as a human knows both are the animals. So cat have four legs, cat have four two eyes, cat can walk. Lion can also walk, can see. It has four legs. So embeddings for both of these can be similar, as you can see from this example. These looks mostly similar, but if we compare embedding of cat and lion with laptop, of course, laptop is not an animal, so embedding for laptop would be different. So we can see all the embeddings for laptop is different. So finally, yeah, all the embeddings are the vectors, but not all vectors are the embeddings, because embeddings actually understands meaning behind the words. This is just a simple illustration how embedding model try to understand the data. So on your left-hand side, we have our training data, and on your right-hand side, we have our test data. So we provide our training data to our machine learning model, and this model will eventually try to understand the words and meaning behind the words. And upon providing the test data that can be seen on our right side, we can clearly see that our embedding model has successfully able to link the word learning from left-hand side to right-hand side with another words, learning, machine, supervised, unsupervised words, and we can see that both are the similar looking words and similar looking words and similar to learning that we train our machine learning model on our training data. So as for now, there are two major embedding models that we use to generate the embeddings. One is from OpenAI, and and other is from Hugging Face. So we have just seen that in my example that I have used text embedding AD8002. We generate dimensions up to 1536 dimensions dimensional data. And the other embedding model, text embedding 3 large, that is also provided by OpenAI, but it can generate embeddings up to 3000 dimensions as well. But there is a caveat to this. OpenAI's these both models by OpenAI are not freely available. So we actually have to subscribe for this, and we actually have to pay in order to use these models. But if you are looking for some open source or freely available embedding models, then Hugging Face can be your friend. It is a platform that host more than like thousands of freely available embedding models. um, so yes, let's now jump into contextual search, and let's explore this contextual search world. Um, on your screen, you can see I have performed a Google searches against two words. On your left hand side, I have performed a Google search of word apple weight, and on our right hand side, we can see I have performed a Google search of apple revenue. Um, Now, if you look at your left hand side, we can see Google has successfully identified that if the word apple is followed by the weight, then it must display the weight of the weight of it must display the apple's fruit weight, right? So it displays the weight of the fruit, and on our right hand side, we can see that if I perform Apple revenue, so Google is sufficient enough to see, okay, if word Apple is followed by the word revenue, that it must display the revenue of Apple company. So it successfully displayed the revenue of Apple company's revenue. Uh, So that actually means that we are performing searches based on true meanings of the words, not by just words themselves. Uh, yeah. So let's now see the workflow of how pgvector actually work. So first of all, we have our original data that let's say we have our original data in the form of text. So we call it as a content. Um, we use just like I gave you an example of Earth is 4.5 billion years old. So this sentence is my original data, and I use the embedding model provided by OpenAI to actually generate the embeddings for my original data. So we have our content first, then we use the embedding model to generate the embeddings, and then once we have the embeddings, we then use these embeddings and store these inside in our vector database, or especially pgvector. Um, so this is simply a diagram that how we can actually store the embedding inside our database. So let's say if user sends a search query from application, what will happen to that search query? In our previous examples, if let's say user says how old is Earth, then we will have our content, that question. We will use again the same embedding model that we used earlier to generate the content embeddings. We will pass the search query that user has provided to embedding model. It will again generate the embeddings for the search query. We will and then once we have embeddings, then we will pass the search query to our database in order to perform similarity searches. And once we have our top maybe 5 to 10 top similar results, we can just pick our topmost similar result and send it back to the application or eventually to the user. Um, so there are a couple of such techniques that we used in pgvector in order to perform similarity searches. First one is L2 distance, that we call it Euclidean distance. That actually measure the distance, straight line between 2 points. We will try to understand these examples, these terms with examples. And the other technique that we have is cosine distance, that angle that measures the angle between the vectors. So let's try to understand L2 and cosine distance with the help of example. So down the below, you see I have two images, one for a toy car and one is for a toy spaceship, you can say. So if we apply L2 distance on this example, that okay, L2 distance might say the shape is different. So of course, car's shape is different from the other spaceship. So L2 distance might say the shape is different. The both are the different things, which is fine. But uh, uh, if we apply cosine distance on this example, uh, cosine distance might say, okay, the shape is different, but eventually both are the toys, so they fall in the same category. So I will say both are the same things. Now we have L2 distance saying these things both are the different, and cosine distance that is saying that both are the same things, because of course it is saying category is same. But uh, we have another technique called inner product, that actually measure the projection of one point to the another point. So let's try to uh, implement the earlier techniques, L2 distance and cosine distance, on this example. Let's say I have two cars, two toy cars. One is on my left side and on my right side in a red shape. If I apply inner, let's see what happened if I apply L2 and cosine distance on this example. So let's see, if we apply L2 distance here, it will say shape is same and shape is similar. So I will say the both things are the similar. But if we will apply cosine distance on this example, cosine distance might also says, okay, shape is different, category is different. So I will say this is different. Sorry. So if we apply cosine distance on this example, cosine distance might say the shape is same, the category is same. I will say this is the same thing. But if we apply inner product on this example, inner product might say the shape is same, but and the category is of course same, but eventually color is different. So I will say inner product might say color, they both are the different things. This is how these three techniques works to perform similarity searches. So yes, understanding each technique will surely help us to ensure our search experience. Now we have two types of indexes used in pgvector. The first one is IVF flat index and the second one is HNSW index. IVF flat index was first introduced in pgvector 0.4, and it is used to perform approximate neighbor search. Um, which means that if we apply this index on our table, on our column, it will always try to retrieve closest possible vector against a search query, because of course this is an approximate neighbor search, not exact neighbor search. Uh, and of course it is approximate neighbor search. The search time will be much faster. And of course, it is IVF flat is a list-based algorithm. We will go into core concept of IVF flat in our next slide. We use the concept of centroids and cluster to build an index. The one thing is IVF flat is suitable for the environments where data is not added or that added or modified less frequently. Uh, and the other index type we have in a pgvector is HNSW index. It was first into it is actually introduced in pgvector 0.5 release, and it is also approximate neighbor search, means that it will give you approximate answers, not the exact one maybe. And it is a graph-based algorithm. Again, we will go into its core concept in our next slides. And it is of course suitable and recommended by the community to use by default in pgvector, because it is suitable for environments where data is changing more frequently. And of course it gives better recall as compared to IVF flat index. um, this is the core concept of IVF flat, how it actually works, and how we actually generate this index. So I have three diagrams here. On our very left hand side, we can see we have simulate our data points into two-dimensional array, two dimensions, where all the dots you see on your screen are eventually your data points or vector data. In your middle diagram, we can see each and every data point is then assigned to its centroid. So we calculate centroid for each data point and assign it to its nearest centroid. And on our very right hand side, we can see all the data points are assigned to each centroid, and then we eventually ends up having like 1, 2, 3, or four zones. So we have our data points scattered in our four zones. Centroid is nothing but just a list of its nearest vector datas, vector yeah so its nearest vector data. So it maintain a list of its nearest vector data. If we go to our HNSW index, and this is the this is the image that shows how actual HNSW index works. So basically, this is a graph-based index, and we use multi-layered graphs. So in this diagram, we can see we have a couple of layers, layer 0, 1, and 2 being the entry point. So all the data points are linked to each are linked to its nearest data points, not only vertically but horizontally as well. So we can see on our layer 2, we have our data point, and nearest vector to our entry point is linked to its entry point as well, and its closest nearest vectors horizontally and vertically as well. So this is how we actually form a graph based structure. This is also suitable to perform quick searches, because in this example, if we need to search a vector that is reside on layer 0, so we will always start from our layer from entry point, which is on layer 2. We will traverse to our its nearest vector, which is on layer 1 down below, and then we will then again try to find its closest nearest point to our search query, which is, of course, we know that will be on our layer 0. So in this case, we will almost skip like 50 or 60 or even in 70% of the matching other vectors. um, and yeah, this is the actual core concept of how HNSW index work. So there is a parallel index building support was recently added in our HNSW index. So what with parallel index building, we can actually spin up multiple workers in order to build the index, and it is more, of course, performance efficient, as we can see from our graph below. So if we use so let's say if we are using 0 workers, so by default its value is 2. So let's say if there is a single thread that is being used to actually build the index, the time it would take might be like closer to 1.5 or 2 hours. But if we use two workers, the time we can reduce up to 30 or 40 minutes as well. And similarly, if we are using 8 workers in order to actually create the index, the time can be reduced, as you can see from this image, to 20 minutes as well. So there is a huge performance difference by using parallel index building. One thing to mention here: workers are just like your what workers are just your CPU cores. That how many cores you want to use to perform parallel index building. Um, RAG. Okay, so this is a kind of a concept that we actually use to perform similarity searches. And this actually enhance our ability to perform similarity searches. So let's try to understand RAG from this example. First of all, we have a user that can send any search query to our database. Let's say, oh, we have a database that hold all the cities information, all the cities all that can hold information of all the cities in Pakistan, let's say. So let's say if a user came and sends a search query to our database, we will first pick this search query and send it to OpenAI or any embedding model to generate the embeddings for that search query. Once we have the embeddings, we will use these embeddings and go to our database to perform similarity searches. Once we have our top 5, top 7 similar searches, we can pick the top most similar search, or we can combine them. And then once we have the similar search for that initial search query, we will just combine both of these search query and retrieved result from the database and passed it again to our maybe you can say LLM or chat GPT in order to generate more accurate results for our initial search query. And once we pass all the information to OpenAI or our LLM model, and it will eventually give us a final result, a final information about our initial query, and then this final result can be passed to user or application. Um, so this an example for this can be let's say if we have a database that holds all the cities information of Pakistan, um, a user can come and say tell me how many airports are there in Islamabad. So Islamabad is a city, capital city in Pakistan. We can just pick this query, how many airports are in Islamabad. We will pass this query to OpenAI embedding model. We will generate the embeddings, pass it to the database. So our database, there is a possibility that our database might not include the exact answer for this query. Maybe there is one airport, there is two airport. We human being can know, but our database there is a chance that our database might not have that accurate number information inside it. So, but there is a possibility that if we have information regarding Islamabad, so there is a possibility that we can have airport name or anything regarding airport in our database. So we will just pick this information, pass it to our LLM model, and this LLM and we will say our LLM model that okay, this is the initial search query, how many airports in Islamabad, and this is the result that we found from our database. This is the result that we found from our database, and it has information regarding airports. So now answer it accordingly. Now that LLM model will actually use to process this information, and eventually can end up having saying there is only one airport, there are two airports, and we can pass that result to the user. There are a couple of use cases why we are actually want to use pgvector or AI in our application. So if we are looking to perform similarity semantic searches, recommendation systems, or if we are looking to build recommendation systems or anomaly detection systems or image search systems, then we can of course use AI or pgvector inside Postgres. Example for a recommendation system could be just like YouTube, where we monitor the behavior of a user, and we suggest similar looking videos, audios to the user that he or she is already listening or watching. Or we can even recommend similar looking movies to a user. And with the image, we of course everyone use Google images, Google searches to get the more similar images. So this is just a simple behavior that we can use. We can build a system that can take a picture from a user and perform a similarity searches on this image and retrieve the more similar images to the user. And if you are thinking to integrate AI into your applications, there are a couple of questions that you might need to ask yourself. If you are dealing with large amount of unstructured data, so unstructured data is of course images, text, audios, or videos. If you have all of these this type of data inside your database, um, uh, of course, this can be a one example to use or implement AI. And is if you are planning, if you are searching the data and comparing performing similarity searches, and that is quite slow for or inefficient, then of course you can use pgvector. And the other things can be if you are looking, of course, to perform searches based on real meaning of the words, but not words themselves. So, of course, pgvector can be a very helpful tool in these type of scenarios. There are few alternatives for pgvector. One is pgvector.rs and one is Lantern. Uh, these both tools are open source and their claim to fame is like they claim to outperform pgvector in index building. So they claim to be much faster than pgvector. So there are these tools that can you can also explore. So that comes to an end for this presentation. I will hand over to Annie now.
All right. Thank you so much, Sima, for that insightful session. We have a few questions. So starting with the first one, does pgvector have parallel index build enabled by default, or do we need to activate it manually?
Um, okay, so yes, pgvector has parallel index building support. We actually need to enable it by, so there is a property named max, if I remember correctly, max parallel maintenance worker inside postgres.conf file that reside in your data directory. You can specify number of how many number of cores that you want to use in performing parallel index building. So you can specify 2, 4, 6, or 8 depending on how many cores on your system you have. So this is how you can actually turn this feature on.
All right. So the next question is, what makes pgvector a compelling choice despite the existence of other dedicated vector databases?
Um, okay. So yeah, we have some dedicated other vector databases, but the one thing is for sure that we can store our original data alongside side with our vector data inside the same database, of course. And I'm pretty sure that this type of other databases does not provide this type of functionality to store your original data with alongside with your vector data. And the other thing can be if you are already familiar with the Postgres ecosystem, you know how to install Postgres, you know how to actually connect to Postgres, you know how to actually run a couple of queries. Then there is no need to actually learn go and learn to other database other dedicated vector databases. So in this type of scenario, you can of course use pgvector as well.
Okay, so the last one is a mouthful. Um, in your example, you created embeddings using an OpenAI model that outputs more than 1,500 dimensions. Does this mean that all the numbers displayed on your screen represent over 1,500 individual characters?
Okay. So I think this is related to the example that I have shown here. So that 1,500, so the model that I have used here is this one from OpenAI. This actually generate dimensions up to 1,536 36 dimensions. So this number is not these characters or numbers one by one, but so if you see, this is a floating array of floating point numbers. So if I highlight this index 0, this is your first dimension, and this is your second, and same goes for all of these indexes. So you have total number of 1,536 indexes in this array. So if I go all the way down till here, you would actually end up having 1,536 indexes in this array. So with dimensions, we actually means number of indexes in our array. Yeah.
Okay, I think then we can move on to the next slide.
Sure.
All right, so if anyone has any additional questions, please reach out to us. We will get back to you as soon as we can. We have our upcoming webinar on explain plans in query optimization in Postgres on June 5th. So I am going to share the link for the registration page in the chat. You will have that by now. And that's about it. Thank you so much, Emma, for the lovely presentation. And thank you, everyone, for tuning in. Have a wonderful rest of the week. Bye-bye.
Thank you.